Okay, today we're going to be doing binomial distributions. So, in the previous lesson we talked about probability distributions, and probability distributions are just descriptions of all the probability of all the possible results of a given probability experiment. And a binomial distribution is a special one. So, and if it turns out that something is a binomial distribution, then there's going to be some formulas that let us calculate some things and make things faster. So there's nothing, either it's a binomial distribution or it's not. If it is, then we have some formulas that let things go faster. So it's a binomial distribution if three things are true. So there's three clauses. And so the first clause is there has to be repeated trials. The second clause is that there's only two outcomes. Now, when I say there's only two outcomes, there could be, for example, many outcomes. What it means is that we could characterize them into two outcomes. And in fact, what we're going to do is we're going to call one of the outcomes a success, and we're going to call the other one a failure. But that really has nothing to do with anything. It's just the name we assign to it, right? So I could roll a die and I could say that even numbers are a success and odd numbers are failures, and there's only two possible outcomes for rolling a die. And then the last condition is that the trials must be independent. They must be independent. Which that means that the probability of success in every single trial remains the same. So if you have a probability experiment where you have repeated trials, there's only two outcomes, or we could classify it as only two incomes, and the trials are independent, then we're going to say that it's a binomial distribution. So let's go through some examples. We're not going to actually calculate the probability. We're going to calculate, we're going to determine whether or not it's a binomial distribution. So for example, let's say we draw 6 cards from a full deck. What is the probability that 3 of them are hearts? So we draw 6 cards from a full deck. What's the probability that 3 of them are hearts? So, what's a trial? So we need to talk about things as a trial. Now, a trial is going to be a single thing. It has to have only two possible outcomes, and it's going to be something that's repeated. So the trial in this case is going to be draw a card. That's going to be the trial. And then the number of trials. In this case, we're drawing 6 cards, so the number of trials is going to be 6. So there's 6 trials there's 6 trials in this experiment. And there's going to be 2 outcomes. And what we're going to say is and in order to show that there's 2 outcomes, we're going to have to define what a success and a failure is. And success or failure has nothing to do with real life success or failure. It's just, again, a name we assign to the 2 different outcomes. So success is going to be card is a heart. Here, let's write that in pretty color. Card is a heart, and a failure would be card is not a heart. Okay, so we have repeated trials. There's 6 trials. There's 2 possible outcomes. It could be success or failure. And then the last thing, is it independent? So is it independent? So the probability that the first one is a heart is going to be 13 out of 52, right? So the first one is, don't write this down. It's going to be 13 out of 52. And then the probability that the second card is a heart, well, it's not going to be 13 out of 52. It's either going to be, if we pulled a heart the first time, it's going to be 12 out of 51. Or if we didn't pull a heart the first time, it's going to be 13 out of 51. But either way, the probability of the second trial being a success depends on the results of the first trial, which means that the trials are not independent. So no, it's not independent. Therefore, it's of course, not binomial. It wasn't that sad. Example 2. So let's say, for example, we have coins in our pocket. So we're going to say we have, we're going to say we have 9 nickels, 11 dimes, 2 quarters, and so what we're going to do is we're going to we're going to draw a coin. We're going to mark down the value and replace it back in the pocket. That's what we're going to do. So we're going to draw a coin. For each trial, we're going to draw a coin, mark down the value, and replace it back in the pocket. And so the question is, what is the probability that if we draw 7 coins, so we do this thing 7 times, the total value will be between 45 cents and 55 cents. And again, we're not going to be solving this thing. We just want to figure out if it's binomial and if we get to use funky shortcut things that I haven't even shown yet. So, so what would a trial be? A trial would be draw a coin. Number of trials is going to be 7. So do we have the repeated trials? We do. Are they independent trials? All right, so the probability of getting a nickel the first time would be 9 out of 22. The probability of getting a nickel the second time would still be 9 out of 22 because we draw the coin and we put it back, right? So is it independent? Yes, it is independent. Okay. So then what are we going to call a success here? So is a nickel a success, dime, quarter? And here's where we run into trouble because we don't really know in a given trial if something is a success or a failure. We don't know how many successes we're supposed to be counting. So can we when we want to talk about it in terms of success failure, we can't do that. We can't describe this problem in terms of successes and failures. Therefore, not binomial. Okay. It's third time the charm. An egg has a 75% probability of being fresh. If you have 5 eggs, what is the probability that exactly 3 are fresh? Okay. So, a trial here would be check an egg. Number of trials. Let's see, do we have our repeated trials? Yep. So we have 5 trials, so it's 5 repeated trials. Could we describe it as a success or failure? I'm going to say success is egg is fresh. And a failure is going to be egg is not fresh, I guess, or rotten. Egg is not fresh. Is it independent? So the probability of the first egg of being fresh is 75%, and the probability of the second egg being fresh is 75%. So yes, It is, which means this is binomial. So this problem is a binomial distribution. Okay, so what we're going to do now is we're going to create some formulas that we're actually going to solve this thing. So we're going to solve this problem now. It's binomial and we want to see something. So let's say, for example, I want to know, let's say I want the eggs to be fresh, because they need to get exactly 3 fresh. So fresh, 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 rotten, rotten. And I want to know what is the probability of getting fresh, 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 rotten, rotten in that order. So I want to do it in that exact order. And so that's going to be, probably the first one is fresh is 0.75. The next one fresh is going to be 0.75. The third one fresh is going to be 0.75. The probability of being rotten, ours are rotten, I should have said that. Probability of being rotten is, well, if it's not 75%, so it's going to be 25%, 25%. Is that off the thing? It is. Okay, so we should probably write it in a shorter, convenient way. So another way of writing something multiplied by itself, we could say it's 0.75 cubed and 0.25 squared. Okay. Now what we want to do is, though, that's not the only order it could come in. I mean, so here, this is the probability of having fresh, 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 rotten, rotten in that particular order. But the fresh could come in any order. So how many orders could we do it in? So we're lining up 5 things where 3 are identical and 2 are identical. So the number of orders, as you may or may not recall, so the number of orders is going to be 5 factorial over 2 factorial, 3 factorial. Or another way of looking at it is we have our 5 locations for the fresh eggs, and there's 5 choose 3 ways of selecting the 3 locations for the egg to be freshened. And 5 choose 3 turns out to be 5 factorial over 2 factorial, 3 factorial. Or we could say we're choosing 2 of the locations for it to be rotten, which would be 5 choose 2, which would also be 5 factorial over 2 factorial, 3 factorial. So what this means is, I'm going to have to go on to another page. What this means is that if I say that x is the number of fresh eggs, then the probability that the number of fresh eggs equals 3, which is what the question was asking for, we're saying what's the probability that we have exactly 3 fresh eggs, is, it's going to be this probability added up this many times, or this times that. So it's going to be 5 choose 3 times 0.75 to the 3 times 0.25 squared. And that's the probability of getting 3 fresh eggs, given that there's a 75% probability that each egg is fresh. Okay, so what we're going to do now is we're going to turn this into a formula. So we're going to create some variables. So the variables we're going to create are n is going to be number of trials, and p is going to be the probability of success. So it's the probability that one trial is successful, not the probability that the whole experiment is successful. The probability that one trial is successful. Q is going to be the probability of failure. And then X is going to be the number of successes required. So what we're going to have now is, let's figure it out. So in this particular problem, the number of trials was 5, and the probability of success was 0.75. The probability of failure was 0.25, and the number of successes required was 3. So I'm going to kind of look over that, and so if I wanted to make a formula out of this, it's going to be looking up the probability that x is equal to 3 equals, so 5 choose 3, that looks like n choose x, so it's going to be n choose x times the 0.75, that was the probability of success, so it's going to be p, and to the power of the number of successes we want. It's going to be p to the x times the 0.25 is the q, And 2, where did that came from? It came from everything that wasn't a success, so it's going to be n minus x. And this over here, this is the formula that you could use to calculate a probability if something is a probability distribution. Now, the way it's actually usually written, in a slightly more confusing but more accurate way, is that we usually say the probability that x equals x. So the probability that the number of successes required is equal to the number of successes that are required is n choose x, p to the x, q to the n minus x. And there you go. So x is the number of successes required in the probability in the problem. So the next video will have examples.